Hello, Robin here. We're going to look at Dijkstra's algorithm. So Dijkstra's algorithm is a shortest path algorithm. In other words, we're going to use a graph and we want to traverse a graph. We're going to fundamentally use a breadth first traversal here. So if you aren't sure what that is, then what I would recommend you do is go to the graphs video I've got within the data structures playlist and watch that first so that you understand what a breadth first traversal is, and then come back to this. If you're not really sure what that is, it'll make this much harder to understand. I'm also going to look at an A-star algorithm, which is just an kind of a more in-depth version of Dijkstra's really, but I'll come back to that more later on. So this video is appropriate for OCR and AQA, any of the A-level related exam boards. Okay, let's have a look at them. So, Dijkstra's algorithm, what's the point? It's to find the shortest path through our nodes on a weighted graph. And in other words, we can represent a distance between those two graphs and say that that's the cost of travel. Why would we bother doing this? Well, it's useful for obviously satellite navigation, but also useful in networks. You can work out data transfers and also work out therefore why you've got a slow network, and you can look at ways in which you can improve and speed that up. Okay, so we've got a graph here. You can see we've got our nodes and our edges, and then on each of our edges we have this value, and that's what I'm talking about, being the cost of getting there. So in other words, to get from A to B comes at a cost of 4. And again, that 4 can represent whatever we want it to. Like I said, petrol, it can be time, miles, whatever we want it to be. So our algorithm, therefore, is to look at each node to weigh up what the closest nodes to it are, and then consider the distances accordingly. So let's have a look then. So from A, you can see that I can get to 3 possible nodes, B, C, and D. If I look at B, first of all, that would come at a cost of 4, which is less than infinity and therefore cheaper. So in other words, I can get from A. I look at C, that would be a cost of 7. And from D would be a cost of 3. There's nothing more I can do now from A, so therefore I consider A to be visited. What I then do is look at this and look for my next shortest path, which is currently D, so I'm going to go to D next. Okay, so at D, we're looking at this, and from D we can get to A, B, and C. We're trying to work out the shortest path from A to E, so it's pointless going back to A. It's not going to be quicker, is it? So I'll ignore that one. But let's look at B and then C. So what we're going to do here is, because we're at D, we've already got a cost of 3 included. So we're going to add that cost onto any of those other routes. So in other words, the 3 plus the 5 will be 8, and therefore 8 is more than 4, and therefore isn't quicker, and therefore we'll ignore it. We then look at the 3 again and consider between the D and the C, so another 3, so in other words a cost of 6, and that is cheaper. So we're going to replace the 7 with 6 and replace the A here with D. There's nowhere else I can go with D, and therefore I've finished. I visited it, so just mark it off. Okay, let's go to B next, because that's our next shortest route. So from B, I can get to D, C, and E. So we look at D first of all. That will be the cost of the original 4 plus that 5 there. So that's 9. So that's not cheaper. So ignore that. We can go from B to C. So a cost of 6. And notice that's actually the same as our current cost. So what we can write here is or B. And again, it's still 6. That's realistic, isn't it? Quite often in life, you can take 2 routes to somewhere and it just costs you the same. And therefore you just have the choice on the day, don't you? Again, finally with E, that will come at a cost of 11. And therefore, just fill that in. We now can't go anywhere else from B, and therefore I've visited it. We move on to our next shortest path. So that's, next nearest node. So therefore that's C. And then again, from C, I can get to D, B, and E. So let's look at our route to B. So you can see I've currently, to get to C, it costs me 6 there. So we're going to add that to these routes. So the 6 plus the 2 to get to B there will be 8. And that's more expensive, so we're not going to do that. I've got 6 plus 3 to get to D, which would be 9, which again would be more expensive. And then finally, I've got 6 plus 3 to get to E, which is actually cheaper, isn't it? So therefore, I'm going to do that. So therefore, that is cheaper. Nowhere else I can go to from C, and therefore, we visit it. Finally, we're at E. From E, there's nowhere to go, and therefore, there's nothing to add to the table other than to mark that we've visited it. In other words, because we have now visited every one of them, we've completed it. What that means then is we can work out the shortest path, and we use this like a linked list. So in other words, we're trying to get from the shortest from A to E. So if I go to E here, E came from C. C came from either D or B. I'm just going to pick D just for sake of argument. Therefore, go to D. D came from A, and therefore A doesn't have anywhere else to go to, and therefore is the end. So in other words, the shortest way is to go from A to D to C to E, or A to B to C to E as it's written there. Always, I recommend always writing out this at the end of whenever you've done this, particularly in an exam. Quite often the question is asking for that, and if you don't write that out, you'll lose marks. So that's a Dijkstra's algorithm. Our second algorithm, as I said, was an A-star. An A-star is special because it allows us to add in a heuristic. A heuristic is just a best guess. We're trying to make this more realistic now, more real-worldly. So, for example, if we were using our edge value as time, what we then could say is that because of a particular route has a lot of traffic on, it therefore usually takes 5 minutes longer than you would want it to. In other words, we then add on an additional 5 minutes to our normal standard time, and that should give us a more accurate prediction of that particular route. So again, what we're going to do is we're going to do the same thing as we did with Dijkstra. So we're going to look at each of our next nodes, but as I said, we're going to consider this additional heuristic value. You can have more than one heuristic if you wanted to, but what I would say is that you should always underestimate with a heuristic. We don't want wildly massive values. The way this works then is we've got our graph, as you can see on the left hand side. We've got our edge values in black, just as we've been dealing with normally in Dijkstra's, but you can also see there's some red ones as well next to each node. They're the heuristic value. So we're going to add that to the calculation as we go along. With these, you can actually write them in straight away, and you can see they're already filled in into the table. So it's really useful and really quite easy for us then. All we're going to do now is just do normal Dijkstra's, but adding in that heuristic. Okay, so we're going to start with A, and from A I can get to B, C and D. So we'll look at B, that comes at a cost of 3. I can look at C, which is a cost of 4. And I can look at D, which is a cost of 2. What we then have is we can add these together. So therefore we have a cost of 7. So the 3 plus the 4, yeah. The 4 plus the 2 and 2 plus the 5. So 6 and 7. And again, they've all come from A previously. Nowhere else we can go with A, and therefore we visited just like we did in Dijkstra's. Okay, let's move on. So we're going to pick our next one, which will be C. C is our next shortest path, and again from C we can get to B, D and E. So again, let's go through them. So what we're going to do here is we don't add on the heuristic as we pass through. We only add the end one on, hence why again it's already written into the table. So in other words, when we check for C, we already have the cost of 4 there. We're then going to add on the additional 2, and then we add on the 4. So in other words, we've got 4 plus 2 is 6, plus the other 4 is 10. To get to there is way more expensive than 7, and therefore we can ignore it. We look at going to D then. So we start off with our original 4 plus our 3 plus the 5. So 7 plus 5, and therefore 12, and therefore again isn't cheaper, isn't better. We then look at our other one, our E. So we've got 4 plus 4 plus the 1, so therefore 9, and that is cheaper, isn't it? So therefore I'm just going to fill this in. So 4 plus sorry, not 4, the 8 plus the 1 is therefore 9, and therefore that will come from C. And again, done all of the C, and therefore just mark that off. Okay, so now we're at B. So with B, we will consider the original value we had plus, again, moving on. So from B, we can get to both C and D. To get to C, we'll come as our 3 plus the 2, so the 3 there that we had, plus the 2 as well, so therefore a cost of 7. So to get to C is 7, which is more than the 6 that we already had, so we're going to leave that. We then look at the D, so is the 3 plus the 4 plus 5, so 7 plus 5 is 12, so to get to D is a lot more expensive. We're just going to ignore it and leave it. In other words, we visited C, we didn't make any changes to the table. We then go to D, which is our next smallest. So again, from D, I can get to B, C, and E. So to get to B would be a cost of 6, plus the 4 would be 10, which again is more expensive, therefore we're going to ignore it. You can get to C, which would be a cost of 2, plus the 3, plus that 2 there. 2 plus 3 plus the 2, so therefore will be 7, and therefore, again, is more expensive, so we'll ignore it. And I can also get to E, which would be a cost of 2, plus 4, which is 6, plus 1, which is 7, which is cheaper, and therefore we'll replace that. So therefore we've got a cost of 6 for the path, plus the 1 is 7, and therefore it's cheaper to go from D, or shorter path to go from D. Done all the ones at D, and therefore we're done. We then look at E. E is the last one, and therefore we know where to go, so we've already visited it. And again, because we've completed them all, we've now completed the algorithm. Again, what we want to be able to do is work out the shortest path from A to E. And again, we treat this just like a linked list, and therefore E came from D, and the D will go from the A, and the A has a null value, and therefore is the end. So in other words, the shortest path from A to E is A, D, E, as it says there. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful, and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.